Welcome to what is lecture 7, and in the next few lectures we shall be discussing electromagnetic waves. We have already seen a little bit of how these waves are formed from Maxwell's equations in vacuum. And first today I'm going to be reminding you of that. So quickly, let's look at Maxwell's equations. Actually, let me just restart once. Yeah, so Maxwell's equations in vacuum, they are given straightforwardly by del dot E equal to 0, del dot B equal to 0, del cross E minus del B del T, and del cross B equal to mu naught epsilon naught del E del T. In our more fancy relativistic language, this is just del mu F mu nu is equal to 0. But now what we showed you before is what you can do is you can start off by looking at del naught. So you can start off by trying to take this second derivative of say the last equation, and that becomes, so this is del del T of del cross B. Essentially, that boils down to curl of del B del T. Now you use the equation in front of that to write this as curl of minus curl of E. So now you use curl of something, the formula for curl of something. So this becomes gradient of the divergence of E plus del squared E. Now divergence of E is equal to 0, so the gradient of divergence of E is equal to 0, so this just gives you del squared of E vector. So this essentially boils down to del squared E vector is equal to 1 over C squared del to E del T squared. Similarly, you also have del squared of B vector is 1 over C squared del to B del T squared. Okay, so these are our wave equations. So now what we want to do, we want to solve the wave equations. Okay, so let's call this solving the wave equations. Now you need to keep in mind that what we had is we had two separate wave equations. So two separate wave equations, one for E. So there was one for the electric field and one for the magnetic field. So you can solve them independently, can be solved independently. But you also have to keep in mind that the solution which arises from it has to obey Maxwell's equations. So this relates the electric and magnetic fields. So solution needs to obey Maxwell's equations. So these are not independent, so this relates E and B. Okay, so now let's try and see how this is the case. And for that, what we are going to be doing is we are going to be looking at a special class of solutions. So look at an example. So this is a special class of solutions where waves propagate in the x direction but do not depend on y and z. Okay, waves propagate in x direction but don't depend on y and z. So these are called plane waves. These would be plane waves because by construction, E and B will be constant in the yz plane. These are plane waves. So let me write this down. Plane waves E and B are constant in yz plane. Okay, so for fixed x and t. So that's the class of things that we are going to be looking at. So now let us try to look at this let's try to look at the Maxwell's equations. So what do we have? We have del dot E is equal to 0. And del dot E is equal to 0 means that E of x in this case, so E of x has to be a constant. Remember, the rest of the things are automatically equal to 0 because E does not depend on y or z. Now this means so E of x is so E is constant in this case. Now what you can do is you can always add any constant electric field as a solution to Maxwell's equations. So what we can do is we can without any loss of generality, we can choose this constant to be equal to 0. So choose set equal to 0, set to 0 without loss of generality. Okay. So now we are going to look for solutions of the form. Look for solutions of the form E is 0, ext 0. Okay. So one thing that I should emphasize here is that the fact that I've chosen the z component also to be 0 is is a choice. I could have made it more general, but remember that we are looking for a specific example here. Okay. So now, the wave equation, so E xt satisfies the wave equation. So the wave equation is 1 over c squared del to E del t2 minus del squared E is equal to 0. Okay. So now what do we have? Del squared E is just so there's only this spatial derivative in the x direction because the other ones are 0. So what you have is now E, so the most general solution solution to this is E of xt is f of x minus ct plus g of x plus ct. So remember, so the thing to remember that this one is a wave traveling to the right with speed c, and this one is a wave traveling to the left with speed c. Okay. This is because as t increases, x also has to increase to keep f the same, and so yeah, so that's the reason why this moves in one way, and g of x plus ct is something that moves in the other way, but again it's also doing with a speed c. Okay, so that's Ex. So now what we are going to be looking at, so this part is actually going to be simple, very simple. So the most important class of solutions, are the ones which oscillate with a single frequency. Oscillate with single frequency. These are also called monochromatic solutions. So what does this mean? So this means that there will be a single frequency, let's call that frequency omega. So let us now focus on right moving waves, and we are going to make this profile a sine function. We could obviously have cosine waves or other shifts of phase, but we'll be looking at that in a bit, not right away. Okay, so let's look at E. So E is E naught sine of omega x over c minus t. This is also written as E naught sine kx minus omega t. Here k is something which is called the wave number, and you also have omega squared is equal to c squared k squared. This is an important thing. This is going to be called a dispersion relation. Okay, a few other things are important. So omega is essentially what is the angular frequency. The actual frequency is omega by 2 pi, but we will just be lazy and we'll call omega the frequency. T is the time period, and that is just given by t is equal to 2 pi over omega. Lambda is the wavelength, and this is given by lambda is 2 pi by k. Okay, and the other thing that is of importance is E naught, and that we have written above is the amplitude. Okay, very good. Now we want to look at the solution for the magnetic field. Okay, solution for magnetic field. So now what do we have? We have B dot del dot B equal to 0. So in a way very similar to last time. So we're going to Bx is going to also be a constant. And we shall set Bx equal to 0 in the same way that we argued last time around. Now Bx and By have to obey the wave equation, okay? But what has to also, we need to, so okay, let's write this down. By and Bz need to obey wave equation. But also you must remember that their behavior is going to be dictated by the electric field through the Maxwell's equations. So this del cross E is equal to minus del B del T needs to hold. So this essentially means that, you know, B can only be of a form 0, 0, B, x, t, right? Because since E has a form 0, E, 0, so the curl of E, so the ddt of B has to be the, curl of E, and that can only be the that can only have a non-zero Z component. Okay, so this and this B of x is going to be related by the Maxwell's equations to this. So this is just minus del E del x. So this has to be minus k E naught cos of kx minus omega t. If that's del B del t, then what we have is B has to be equal to E naught over C into sine of kx minus omega t. You remember, one has to remember that we have put in the dispersion relation here to simplify this last equation. Okay. So now we see that electric field B, so E and B and E. So let's go with E first. E and B oscillate in phase, but in orthogonal directions. They are also both orthogonal to the direction of propagation of the wave. Okay. So just to give you a picture of this, we just go back to what we had looked at. Here you see that the wave is traveling along the x-axis here, and that's k, and E is perpendicular to that. I mean, oscillating in the y direction, and B is perpendicular to both of them. That's in the z direction. As I said, this sort of forms three mutually perpendicular directions. So we simplified things a little bit by choosing E to oscillate just along the y direction. You could have made things a little more involved by choosing some arbitrary direction which was perpendicular to the x direction. Even then you would have found that B is perpendicular to both E and K. Okay, so that's just trying to it's just a question of trying to rotate the axes, if you wish. Okay, so what we will do next is we will try to look at a few things. So this so an important thing about Maxwell's equations is that it's linear, and because it is linear, we are allowed to add any number of solutions of this above form, the form that we have written down for B and E. So this form and this form. So we can add things like this up, and we will still have have a perfectly good solution to the wave equation. This is essentially something which is called the principle of superposition. Okay, so let me just to make sure that we emphasize this, I'll just write this down for you. Since Maxwell's equations are linear, we can add any number of solutions of above type, and that still would be a valid solution. This is what is called the principle of superposition. And this is something that you have encountered before. So this is also a particular important property in the context of light, because this is what allows light rays traveling in different directions to pass through each other. And very importantly, if you wish, this is why we can see all that we can see. Okay, so all right, so this sort of linearity of Maxwell's equations also encourages us to write down some new new notation, which might actually sound a little strange. Look a little strange at first. Okay, so what we are going to be doing is we are going to be using complex analysis. Okay, complex notations. So we'll write E as, so the thing that we just did, so E y vector, and we'll write it as exponential I k x minus omega t, and we will do the same for B, and we'll just make sure that we just write u z cap e to the I kx minus omega t. So this is the solution that we had before. Now this might sound strange, because physical electric and magnetic fields should certainly be real. And what you should do is you should simply think of the real parts of these above expressions as the actual electric and magnetic fields. Linearity of Maxwell's equations, however, means that both real parts and imaginary parts of B solve Maxwell's equations. And more importantly, if we add Maxwell's, add these things, complex E and B solutions, then the resulting electric, real and imaginary pieces would also solve Maxwell's equations. So it's going to be very, very useful to just do things in this particular complex notation, because instead it's much easier to look at exponentials than writing down things in terms of sines and causes and multiplying and adding and so on and so forth. Okay, so in order to bypass this trigonometric problems, if you wish, we just go into this exponential formulation. You should, however, keep in mind that this notation also comes with some amount of danger. Is when you compute something that is not linear in E and B, then you should not use this complex notation that I've just said. You need to take the real part first. I'll try and give you an example of this as we go ahead. Okay, but for the moment, what we are going to be doing is that we are going to be writing these things in terms of, complex, guys. Now let's start to look at a more general solution. So let's look at a general solution. And for that, what we will write is E naught vector into e to the power I. Now I write a k vector and x minus omega t, and B is B naught vector e to the power I, again k dot x minus omega t. Okay. E naught and B naught are both complex vectors. So again, we will get the physical, electric and magnetic fields by just looking at the real part of these equations. The vector k is now called the wave vector, and the magnitude of the wave vector is the wave number. Now notice that these equations, this particular equation, this is going to solve, this solves the wave equation if omega squared is equal to c squared k squared wholes. Okay, so this you can just see by just plugging it into the wave equation. Now we need to also look at what is going to happen when we impose Maxwell's equations on this. So let's do that. So del dot E equal to 0. This is going to give you I k dot E naught equal to 0. Del dot B equal to 0 gives you I k dot b naught equal to 0, and del cross E equal to minus del B del T gives you I k cross E naught is I omega B naught. Now you can actually find that the last equation, so this final expression of curl of B would not actually generate anything new for you. I leave this one as an exercise, and what I'm going to be doing in the next 5 minutes is that say a little bit about polarization, which I'm going to be returning to in the beginning of the next lecture again. So let's look at this. So now let's try and interpret these equations that I have laid out for you. So let's call linear. So let's first look at a case where you have E naught and B naught are real. If they are real, so these equations, so let's call this equation 1, this equation 2, and this equation 3. So this is very simple. So what it does is that so 1, 2, and 3 say the thing that we have already learned is that E naught and B naught are perpendicular to K. They are also perpendicular to each other. How do we see that? Yeah, you see that K is perpendicular to E naught by the first equation, K is perpendicular to B naught by the second equation, and K and E naught are perpendicular to each other. So the curl of that being equal to B means that E is also perpendicular to B. E naught is also perpendicular to B naught. So these three vectors, so these vectors form a right-handed orthogonal triad. So the waves of this form are called linearly polarized. Okay. Finally, today, circularly and elliptically polarized. Polarization, circular, let's say circular and elliptical or elliptic polarization. So let's erase this, I'm sorry. Circular and elliptic polarization. So now, so not everything is going to be linearly polarized. So now what we are going to be saying is E naught and B naught are complex. B naught are complex. Let's look at this. So E naught is some alpha minus I beta, where alpha and beta are the vectors. So E is the real part of this, Okay, let's rephrase this. The real part of E is then alpha cos k dot x minus omega t plus beta sine k dot x minus omega t. And Maxwell's equations give you Maxwell's equations. What they do is they say alpha dot k is equal to 0, as is beta dot k. Okay. So now what? So now if we look at the direction of E in some fixed point in space, say, let's take x equal to 0. So we see that this does not point in any specific direction, but it is going to rotate in time within the plane that is spanned by alpha and beta. So let's so the direction of E, at some point in space say yx equal to 0, does not point in a fixed direction. It rotates in the plane spanned by alpha and beta, perpendicular to the k vector. And obviously you can understand that when k is the direction of motion, then alpha and beta will span a plane which is perpendicular to it, and so this is going to change out there. Let's look at a special case. We can choose the phase of E naught equal to e to the power I pi over 4. So that essentially means that this alpha vector and beta vector, the moduli of these are and also take alpha dot beta equal to 0. If you do that, then the direction of E is going to trace out a circle in time. So direction of E traces out circle in time. As you can see that you're going to get a circle in time, and this is going to be so in the plane perpendicular to K, and this is what is circularly polarized light. If it is not, so when you know, when this is not the case, this traces out an ellipse. So this traces out an ellipse. Okay, so let me just get rid of this from this last line. Okay, just give me a second. I need a little bit of space to write this last line. So, okay. So let me just say otherwise this vector traces out ellipse, and hence is called elliptically polarized light. Okay, so we will try and explain this a little bit more in the next lecture. But for now, I just want to leave you with the fact, this is where we want to end. So just a quick recap of what we did. So we started out by looking at Maxwell's equations in vacuum. I showed you again that the wave equation comes by from these. So now there are two separate wave equations, for one for the electric field and one for the magnetic field. So the solution also needs to obey Maxwell's equations. Hence, we are going to be relating E and B in this way. So we looked at an example where the wave propagates in the x direction, does not depend on y or z. These are plane waves. And what we found is that, you know, in this case, so the wave traveled along the x-axis given by k out here. Then E was in the y-axis and B was in the z-axis. These were mutually orthogonal to each other. And so this is what we found. And so then we looked at the case where you know, we just said that we were going to be representing these in terms of complex variables, and that is going to help us analyze things better. So we wrote down a general form of the wave, and then showed you that what restrictions Maxwell's equations brings with it. When we were doing it, when we chose E naught and B naught to be real, then we got something which was plane polarized light. The Maxwell's equations in that case just gave you the fact that E naught and B naught are perpendicular to each other and to the wave vector. And from this is waves of this form were called linearly polarized. And then at the end, we dealt with the fact where E naught and B naught were not real anymore. In that case, we got to things which were circularly and elliptically polarized light. I'll try and give you, if this last bit of the circular and elliptic polarized light was a little too quick, I will try and explain this a little bit more in the next class. So all right, so I'll stop here for now, and then the next lecture will be related to the waves again. We'll be looking at some other aspects of it. All right, thank you. See you.